So, good evening, everyone. I'm Calvin Joseph, and today I'm going to conduct the week 4 problem solving and doubt clearing session for the course State Space Approach to Control System Analysis and Design, which was taught by Professor A.P. Tiwari of IIT Mandi. Okay, so in this class, what I'm planning to do is teach about what is controllability, what is observability, what is the Jordan form, and also discuss regarding stabilizability and detectability. So I have come up with some few example sums which I like to solve, and once so that we can get a work kind of a flow of how to solve sums. If you see a sum, how to tackle a sum, etc. Okay. So let me just first start with some brief introduction. So today is week 4, and we will be considering today. Let's start with the topic of controllability. So we have a system. Okay, we have a system. It could be a LTI system, it could be a linear time varying system, etc. The linear LTI system is given by x dot is equal to ax plus bu. Linear time varying system is given by x dot is equal to a of t into x of t plus b of t into u. Okay, so for let us consider case of a LTI system. Okay, we'll consider case for an LTI system. So in an LTI system, there's a formula to find controllability. We find what is known as the controllability matrix. Q. And that is given by B, A, B, dot A raised to N minus 1 into B. Okay, this is the controllability matrix. And if the rank of Q is equal to N, okay, then we say that it is controllable. Then we say that the system is controllable. But if the rank of Q is less than N, then the system is uncontrollable. All right. So these are some initial definitions. So suppose the rank of Q is less than N. So suppose the rank of Q comes out to be N1 when N1 is less than N. Okay. So the rank of Q is N1, which is less than N. Then there is a term known as the controllability subspace. Okay. And that controllability subspace is in N1 dimensions. Okay. It is in N1 dimensions. So, and what is the uncontrollability subspace? That is in N minus N1 dimensions. All right. So this is regarding controllability, etc. So I'd like to point out that, sorry, for the LTI system, we'll consider this A matrix. It is a N cross N matrix. And this B matrix is N cross M matrix. Okay. So in our case, simple case, what we'll take M equal to 1. Okay, so B belongs to R, N cross 1. Okay, so now let us consider the example for the question. So this is my LTI system. X dot is equal to 3, 2, 0, 10x plus 1, 0, u and y equal to 1, 1x. Okay, so x dot is equal to 3, 2, 0, 10 x plus 1, 0 u, and y is equal to 1, 1 x. Okay, so my A matrix here is what? 3, 2, 0, and 10. Hmm? And my B matrix is 1 and 0. And my C matrix is 1 and 1. Okay, so the A matrix dimension is 2 cross 2. B, because it has 2 rows and 2 columns. B matrix has 2 rows and 1 column. So it is 2 cross 1. So we can do A into B. Okay, so A into B is what? 3, 2, 0, 10, 1 and 0. So 3 gets multiplied by 1, that is 3, and 2 gets multiplied by 0, so it is 0. So 3 plus 0 is 0, 3. Then 0 into 1 is 0, and 10 into 0 is again 0, right? So this has dimension 3, 0. So AB has the dimension 2 cross 1. So the controllability matrix Q is actually given by B and AB, right? So B is given by what? B is 1, 0, and AB is 3, 0. Okay. So now we have found the controllability matrix. So this is the controllability matrix. And now we have to, let us say, we have to find the rank of Q. We need to find the rank of Q is the question now. Or we just want to say whether it is controllable or uncontrollable. So if it is controllable, then the rank of Q should be equal to 2. Okay, if system is controllable. Okay, and in that case, what is required is that a determinant of Q should not be equal to 0. This is a must. The determinant of Q should not be equal to 0. So let us say, so what we want, it should be proved that a determinant of Q should not be equal to 0. So we have to first find what is the determinant. Okay. So in our case, the determinant is what? 1 into 0 minus 3 into 0. So that is 0. So our Q, the determinant of Q is equal to 0. So what does it mean? That the rank of Q is not 2, actually the rank of Q is 1, and hence the system is uncontrollable. Okay, it is uncontrollable. Okay, so any doubts in this till now? Okay, so if there's no doubts, let me further discuss why, what is happening. So we had a page. So we know it is given by x dot is equal to ax plus bu. This is our system, right? And this is what x1 dot, x2 dot. What is the matrix? Let us see. It's 3, 2, 0, 10. So 3, 2, 0, 10 into x1, x2 plus 10, 0, u. Okay, this is plus 10, 0, u. So now what we do is we can write it down as, so my x1 dot is equal to 3x1 plus 2x2 plus 10u. Okay, what is my x2 dot? X2 dot is 0 into x1 plus 10 into x2. So 10x2 plus 0u. Okay, so now what do we see over here? That u has effect on x1. Okay, that is seen from this equation, that if I can change u, and when I control u, u will in turn control x1. It can control x1. But u has no effect on, it has no effect on x1. It has no effect on x1 because x2 dot is equal to 10x2. That is independent of u as well as independent of x1. Just in case, okay, let me just give a fictitious scenario that if it was 10x2 plus x1, okay, assume, just assume, let me write in different color. If it was 10x2 plus x1, then what would happen? Then it would be controllable. Okay, it would be controllable because x1 dot is controlled by u and x2 dot is in turn controlled by x1. Okay, so I can control x2 indirectly using u. Okay, so in that case, what would happen is, what if it was plus x1, then what would happen? This matrix, instead of 0, it would be 1. Okay, it would be 1, right? So let us just quickly, I just show how it would be controllable. So now the new controllability matrix for the new system. So the system has been modified. Okay, the system has been modified. So I will find a new controllability matrix. So Q new is what? B into A new into B. Because B remains the same, but only A has been changed. Okay. So what is A new into B? Is what? 3, 2, 1, 10 into 10 and 0. Right? So that would be 30 and 10. Okay, 30 and 10. So now my Q new is, which is B into A new to B. So that is 10, 0, 30 into 10. So my determinant of Q new is 100 minus 0, it is 100. So it is not equal to 0. That means what? My rank of this Q matrix is equal to 2. So it is a full rank. Okay. So the modified system is controllable. Okay. So the modified system is controllable. So from this, what do we understand is that controllability, use a different color. Control Y. Controllability is very much dependent on A and B. And if my A and B matrix changes, a system which was earlier controllable could become uncontrollable. A system which was earlier uncontrollable could become controllable. Okay. So this is something which we must keep in mind. Okay. So now let us go back to our old original system. Okay. Let us go back to the old original system. Right. And that is, what is the old system? This is the system. Okay. So we have already shown that this is an uncontrollable system. It is uncontrollable. Now, what do we do? Is this system stabilizable? We have to check whether the system is stabilizable, right? So what do you mean by stabilizable? So we have to check whether is the system stabilizable. We have to see this. So for that, we need to find the, we have to understand about the stability. So to understand about the stability. So let us do, this is the A matrix, which is given by 3, 2, 0, 10. So let us find the eigenvalues. What are the eigenvalues of A? So to find the eigenvalues, we will do lambda I minus A. Okay, so this is lambda into 1, 0, 0, 1 minus 3, 2, 0, 10. So that is lambda minus 3 minus 2, 0, lambda minus 10. Okay. So the eigenvalues is found by equating the determinant to 0. So that would mean lambda minus 3 into lambda minus 10 minus 2 into 0 is 0. So minus 0 is equal to 0. Therefore, my lambda is equal to 3, comma 10. So now when my lambda is 3 or 10, 3 and 10, we see that they are positive. First of all, they are distinct. They are distinct, okay, and positive. So if you have a recall, the modes corresponding to these eigenvalues are given by e raised to 3t and e raised to 10t. Okay, these are the modes corresponding to these eigenvalues, and these modes are unstable. Okay, they are unstable because they increase. They are increasing with time. Okay, and they are exponentially increasing. So that means it's very fast increase. What would happen if lambda was -3 and -10? If these were the eigenvalues, what would happen then? The mode should be what? E raised to -3t, e raised to -10t, right? And these decay with time. These decay with time, and these are stable modes. Okay, but this is not the case. So we are considering this case. That means we have the modes e raised to 3t, e raised to 10t. They are unstable. So the system is unstable, right? These modes are unstable. As well as we have found out that the system is uncontrollable. So it is an uncontrollable system. It is an unstable system. So this system is not stabilizable. Okay. So the system is not stabilizable. Okay, it is not stabilizable. We cannot stabilize this system. Now we have found that the system is not stabilizable. Let us consider about the observability. Okay, let us consider observability of this system.
Excuse me, sir. Shall I ask
Yes,
you a
yes.
doubt?
Yeah, you can ask.
Sir, sir, that controllability matrix is like we'll form a matrix with B, A, B, A square, B like that.
Yes, yes.
Can we
Uh-huh.
form a matrix with the elements as A, B, A square, B like that instead of the first column element as B? Can we form a controllability matrix with first element as AB, then A square B?
Yeah, you can. See.
Sir, my question was because there is an assignment question in which it was given a controllability matrix, which was the original controllability matrix B, A, B, etc. A raised to n minus 1 B, and another
Okay.
matrix A, B, A square B, etc. A raised to n B. Then they are asking a question relating to rank of these two metrics, like
Okay.
how that matrix, whether it is controllable or not. With this matrix which you have taught now, can we relate the answer? Because nothing is told in the lecture also, which Prosa has taken.
Okay.
And in the textbook also, no idea is being given relating to. I searched in many of the textbook, but nothing is given
Okay.
relating to a controllability matrix which is formed with A B, A square B, like that. In every
Okay.
textbook, the controllability matrix starts with the first column as B, and then comes the next elements, but no
Okay. Okay. So
data is given
you're
relating.
from you're a PhD student, a master student, or BTech student?
So PhD.
Okay. 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 Fine. So yeah, actually, the thing is, we are not like I am conducting these sessions. I am not supposed to explicitly solve your assignment questions. Okay, so I can just give some hints,
Sir,
right?
I don't need the
Uh,
direct answer. I'm asking
yes, yes,
whether.
yes, yes, yes. Okay, yeah. So you can actually like if it is like this, you're saying that your matrix which they have given is what a b a square b like this, right? Okay, a raised to
Yeah.
nb.
Yes, sir.
So if you take a common, it will become b a b a raised to n minus 1 b, right? You have taken A common?
Yeah. Yes, sir. Yes, sir. Yeah.
Yes. So then this is your controllability matrix, right? So if you can
Controllability matrix.
you can either find the rank of this. So this will have a rank, and this also should have a rank, right? Mm, let me
Okay,
think.
sir.
Yeah. Okay. A into B. So A, I don't think will change the rank. No, A doesn't change the rank. Yeah. So the rank will be the same way. Hello.
Rank of both the metrics will be same.
Will be the same. Yeah. See, actually, we can try this example also. Okay, we'll just try this example. Okay,
Sir,
so
shall I give a request to you, sir?
tell your request. Yeah, yeah.
Sir, whether the assignment questions which has already whose due date is over, can the solution be given after the due date is over? Can the solution of the assignment questions be given so that we'll get the answer? We can prepare it for the end exam. Because in the
Okay.
other subjects we find the
Yeah,
solution,
yeah,
but in
yeah.
the
I
state
was
space, no
also
solutions are being given.
yes, yes. I also was thinking why the solutions are not being provided. So actually, the correct answer is being provided, right? Like after, like I was taking week 1, week 2, week 3. They have told which answer I have put correct and which answer I have put wrong, right?
Yeah,
That
yes,
at
sir.
least is there,
Just a
right?
final answer is only given. That is of no use, sir. We
But
want the steps with which.
solution. So,
Yes.
like yeah, actually, I don't know. I'm not under the professor. Actually, the professor, you'll have to contact him directly because I don't have the authority to
Okay,
provide, and
okay, sir. Okay, fine, sir.
I
Fine.
cannot also
Okay,
say. Okay,
okay,
so like I'll tell like how I am trying to, you know, like even I have to study this. Even I also have to solve the assignments. So I have to also go through the lectures, and I also should
okay.
understand. So what I am trying to do is
Uh,
some of the assignment questions are very big. Okay, they're big matrices, everything. Okay, so I am trying
yeah,
to
yes, sir. Uh,
code it out. Like I am trying to use MATLAB and check whether my answer is correct or not. Hmm. So, like now, let us say this is there,
okay,
right? You want to find if the rank of A B A square B A raised to n B is there, or whether B A B A raised to n minus one B is
okay.
there. Okay, so we'll try. Okay, to
Uh,
just to
uh,
verify. I think they both will have the same rank, but let us verify. Okay, in our case, n is 2. Okay,
sir,
in
sir,
our
but in exam we will not have any MATLAB provisions.
in the exam, yeah, correct. You will not have MATLAB provision, but I don't think in the exam you will get a very complicated thing, right? Uh, in the exam, I don't think you will have to
Okay,
multiply a 7 cross 7 matrix with another 7 cross 3 matrix and another 7 cross 3 matrix and do 7 times those multiplications. All that I don't think will come in the exam. It's not possible, right?
okay,
Because
okay.
how can you do that multiplication, right? Uh, Usually, what I
Yes,
have
sir.
a
It is
feeling
much
is,
complicated. No.
yeah, yeah, it's very complicated. Usually, I have a feeling that it is the hard and difficult things are put in the assignments, and the exam will be usually a bit easier. That's my impression. Hmm. Like anyway, I don't know how this
Okay,
professor
sir.
does. Okay, so yeah, so for me,
Okay, sir.
even I am finding this is quite difficult. So I'm using MATLAB to solve. Okay, and if you like, I actually upload my notes. So whatever sessions I do, the notes I upload, right? So that you can check.
Okay.
Do you know have that link to my notes?
Yes, sir. Yes.
Yes, yes, yes.
Yes, sir.
Fine.
We'll get the notes.
Okay, okay. So my notes are there, and their notes also are there. Yeah, but I acknowledge that it is difficult. So like was last week, they in the assignment they had asked about linear time varying systems, right? You have to find the state transition matrix,
Yes,
you have
sir.
to
Yeah.
find the fundamental matrix, etc. So which was not taught in the week 3.
Yeah.
So I also had to
Yes, sir.
search and found out that Professor Ramkrishna Prasamurthy has a video as an NPTEL course, and that he has considered linear time varying systems. So that link I have put in my week 3 video. So from there, like I have
Okay.
understood how to solve, and then I have also solved it in my week 3. So I think those kind of questions, if you have a doubt, then I think I have already solved it. That fundamental matrix and the state
Okay.
transition matrix for the linear time varying system. I have solved
Okay.
it, and also I've solved it in MATLAB. So how do I know my solution is
Okay,
correct?
sir.
That also I'm trying it in MATLAB. Okay, so this is the way I am verifying, validating my answers. Okay.
Okay, sir. Okay.
Okay. All right. So anyway, just for my satisfaction, let me just try to check the rank of, like the question is what is the rank of BAB, and whether the rank of, so what is the rank of this, and what is
Type of thing where you convert it into
sorry. Okay, and what is the rank of AB A square B? Okay, so let me check. So I've defined my A and B matrices, and let me say my Q1 matrix is given by B and A into B. So this is one matrix, and my Q2 matrix is given by A into B, my A into B. Okay, let me run it, and I've got this. And let me find the rank of Q1 and what is the rank of Q2. So it is coming that both the ranks are same. Okay. So thus we can say that the rank of this AB, that is these ranks are equal. Okay, so that I've just checked in MATLAB. Right? Okay. Then next in the question which I had come up, like we have to determine the Jordan form. Okay, let us find the Jordan form. Because why do we use the Jordan form is because it makes things simple. Okay, we have to find the Jordan form of the system. Okay, so my matrix is given by what? X dot is equal to 3 2 0 10 3 2 0 10 x plus 1 0 u. Okay, 1 0 and u. Okay, so now this is my A matrix, this is my B matrix. Now I want to simplify it. I have to make it in Jordan form. So to convert into Jordan form, what do we do? We have to find the eigenvalues and eigenvectors of A, right? So we have already found that lambda is equal to 3, comma 10. These are the eigenvalues of A matrix. So let us find the eigenvectors. So eigenvector is what? Lambda I minus A, right? So that is what. Um, so let us consider lambda for, sorry. Let us consider that for 3i minus A, okay? For the first one. So that is 3003 minus 32010. Okay. So lambda I minus A would be, it would be 0 minus 2, 0 minus 7, right? So we have lambda I minus A into V bar is equal to 0. Okay. So what do we have? 0 0 minus 2 minus 7 into V11 into V12 is equal to 0. So we get, so from this we get minus 2V11, oh no, sorry, minus 2V12 is equal to 0, or minus 7V12 is equal to 0. This means my V12 is 0. So this eigenvector V1 bar actually is equal to any value. It could be any value except for 0. This is some value x, and V12 has to be 0. So we take it to be 1 0. Okay, if we take it to be, it can also be 10 0 also I can take, I can make it 2 0, etc. I can take. but it should be any x should be any non-zero value. So I'm taking 1, 0. So is there any doubt in this how to find this eigenvector? Okay. So I have found this eigenvector v1 bar. Next, I'll have to find the eigenvector second one. So I'll have to do lambda 2 I minus a into v2 bar is equal to 0. So that comes out to be, that will come out to be 3 lambda 2 is what? 10 into I. So 10, 1, 0, 0, 1 minus a. So there is 3, 2, 0, 10. Okay. The whole into v2 bar. So this gets converted into 7 minus 2, 0, 0 into v2 1 and v2 2 is equal to 0. So we get 7 v2 1 minus 2 v2 2 is equal to 0. Or v2 1 is equal to 2 by 7 v2 2. Okay. So let us put v2 2 to be equal to 7. Okay. Then what do we get? We get v2 1 is equal to 2. Then we get v2 1 is equal to 2. So our v2 bar in this case is equal to 2 and 7. Okay, so this is our matrix, right? So we have a transformation matrix V, which is actually v1 bar, v2 bar, right? v1 bar is what? v1 bar is 1, 0, and this v2 bar is 2, 7. Okay. So what is the inverse of V? Inverse of V actually is what? 7 and 1 get interchanged, minus 2 and 0 be here. You interchange the sign of the off diagonal elements. You do 7 and it is divided by 7. Okay, so this is our inverse matrix of V, right? So that actually is 1, 0, minus 2 by 7 and 1 by 7. So now we are converting to Jordan form. So Jordan form is the diagonal matrix is given by inverse of V into A into V, right? So that is actually what? 1 minus 2 by 7, 0, 1 by 7. A is what? 3, 2, 0, 10 into V, which is 1, 0, 2, 7, right? So this actually is equal to 1 into 3, that is 3, into 0, so it is 3, then 1 into 2 and minus 20 by 7, so 2 minus 20 by 7, so that is 14 minus 20 by 7. Then actually let us do step by step. So 2 minus 20 by 7, this is 0 into 3 and 1 by 7 into 0. So this is 0, 0 into 2 and 1 by 7 into 10. So this is 10 by 7. So this into 1, 0, 2, 7. So this actually is 3. And then minus
Excuse me,
6
sir,
by...
the screen is not visible.
Screen is not visible.
I mean, what you are writing is not visible.
Okay, like, is this visible? Hello, I've written. Is this visible? Or let
Your
me
face is seen
stop.
on the screen, sir.
So my face is seen on the screen. No, you'll have to actually, what you have to do, you have to, there are two options. Either my video is seen or the screen is seen. You have to select the screen. You need to do that. Wait, first let me stop sharing.
Before it was
Oh,
seen, sir, your screen was also seen, but now the screen which you are writing is not seen.
okay, 1 minute. So now I have shared my screen. Now are you able to see?
Yes, sir, now it is visible.
Okay. I don't know what happened in between. Okay, so this is the matrix we are getting, right? So it is 3 minus 6 by 7, 0 and 10 by 7, right? into 1207. So when you multiply this even further, what you will get 3 into 1 is 3 and minus 6 by 7 into 0 is 0. Then this 3 into 2 is 6, right? This is 6 and minus 6 by 7 into 7 is minus 6. So 3 into 6 minus 6. 0 into 1 is 0 and 10 by 7 into 0 is 0. And 0 into 2 is 0 and 10 by 7 into 7 is 10. So this matrix actually comes out to be 3, 0, 0, 10. Okay, so this is the diagonal matrix, right? These are actually your eigenvalues, which are on the diagonal. Okay, so this is your diagonal matrix, right? Similarly, your B, which is a diagonal form, which is on the Jordan form, will be actually inverse of V into B, right? So what is our inverse of B? It is 1 minus 2 by 7, 0 into 10 by 7. And what is B? Actually, it is 1, 0. So now let us find it. So this will be actually 1 and minus 2 by 7 into 0, 0. Then 0 into 1 is 0 and 10 by 7 into 0 is 0. So this is again 1, 0. So BD, our BD remains the same, right? So we have converted it into Jordan form. Okay. So this actually is our Jordan form. Let me give it another variable AD, right? So our new system, our new converted system Z dot, which is equal to AD into Z plus BD into U, that is given by what? Z1 dot, Z2 dot, right? Is equal to 3, 0, 0, 10, Z1, Z2 plus 1, 0, U. Okay. So if you see this, if you write it down, you get Z1 dot is equal to 3Z1 plus U, and Z2 dot is equal to 10Z2 plus U. Yeah, 10Z2, sorry, 10, it's only 10Z2. Okay. Uh, so that's why again that's why it is still uncontrollable. That's why the system is again, you can see it is still uncontrollable because Z2 dot is not controlled by U. So if you write it further, right, you have your U input, okay, that is going here with gain 1, and then you have a summer, and then you have a 1 by S term. It's a 1 by S. That's your integrator. So this actually is your Z1 dot. And this is your Z1, right? And this is 3. So this is your Z1 dot is actually 3Z1 plus U. And your Z2, this is, let us say, this is your 1 by S. This is your Z2 dot, and this is your Z2. This is plus, it is 10. So Z2 dot is equal to 10 Z2. So U, so if you can see, your U is not connected to Z2. Your U is not connected to Z2. That is why it is uncontrollable. You're not able to control it, right? Okay, so any doubts in this? Okay, so this we have found that it is uncontrollable even after transformation. So what is our conclusion? Even after linear transformation, system remains uncontrollable. Okay. So now we'll find the simple thing which is known as the observability. So this is observability matrix. P is what? It is actually C, and it is A in, C into A. Okay, this order is important because C is a row 2 cross 1. No, it is 1 row 2 column. Sorry. So it is 1 cross 2 and A belongs to R2 cross 2. So C into A belongs to R1 cross 2. Okay. So another thing I'd like to say is that the meeting will end in 3 minutes. The Zoom, because this is a Zoom meeting and has a limit. So after the Zoom meeting ends, I will again restart the meeting. So you'll have to again rejoin the same link. Okay. So now C into A, C is what 1 1 and A is what 3 2 0 10. So C into A gets converted to 3 plus 0, so 3. 2 plus 10 is 12. Sorry. That is 3 and 1 into 2 plus 1 into 10, so that is 12. So by observability matrix is C and CA, so that is 1, 1 and 3 and 12. So let us find the determinant of P is 12 minus 3 is equal to 9, which is not equal to 0. That means the rank of P is equal to 2. So it means the system is observable. All right. So we can say that the system is observable. So okay. So we have found that the system is observable, and if it is observable, and it is not controllable, so it is uncontrollable system. So similarly, if it is any system, like you get a second order system, you can find it. If it is third order, fourth order, etc., it just becomes you have to do more matrix multiplications and you have to check it. It becomes a little bit more difficult, right? So what we are seeing is that if you like make it in Jordan form, in this Jordan form representation, it becomes much easier for you to say. Because it is zero, you can, with just seeing the Jordan form matrix, you can say that it is uncontrollable, right? So let us see what happens when we convert this Jordan, when we will convert the C matrix also. So the C matrix actually is given by CD. Okay, so CD is actually C into V. So this actually is 1, 1. B is what? V is V is 1207. So V is 1207. So when you find CD, it is 1 1. So this is 1 and 1 into 2 plus 1 into 7. So it is 1 9. So this is the CD matrix. So if you will, so what is our Y? So the Y is dependent on this CD, right? So now you can see in this CD matrix, there is no zero. So, sorry. In this CD matrix, which is in diagonal form, which is in Jordan form, there is no zero element. So what does this mean? Hence, we can say that the system is observable. Okay, so this is one way. So if you convert a system into Jordan form, it becomes much easier for you to tell whether it is controllable, whether it is observable, etc. It becomes much easier, right? Okay. So let's refer to what sir is shown. Okay. six scores. So we have this system, okay? There's this system here, which is given by this equation, x dot is equal to ax plus b. Okay, so this is a third order system, and you have two inputs are here. Okay, you have two inputs, right? So then what do? You again find the controllability matrix, and you find that the rank of q is equal to 2. This is when you have second rank, right? So what they are doing is they have to find where a transformation matrix. So the transformation matrix is what they're using the independent rows. The independent rows of this they're using, which is 0, 1, 0, 1, 0, 1, they're using. And they're adding a third row, which is not dependent on the previous row. Okay, they're adding their own row. And once they add that row, what they're doing is they're doing the transformation. They're finding the inverse matrix and they're finding the transform system. Okay, and that transform system is made into two systems. One system is the controllable part, another system is the uncontrollable part. So, how do I explain this? Let me show the code which I'm written instead. So this is the A matrix, right? This is the A matrix which is there of this system, right? And this is the B matrix is there of this system, right? So you can run this code. You can write this is the A matrix. We get this the E matrix, this is the B matrix. We are getting these are the matrices, or better, let me just show one by one. Okay, so let me run it. So you're able to get the A matrix is given by this, B matrix is given by this, right? So now if you want to use MATLAB or something, you can find the control to matrix. You have B, A, B, A, A, B. Okay, you can run this section. You will get Q matrices come out like this, which they have also got, right? Now you have to find what is the rank of Q, right? So there is a command rank of Q. You will immediately get your rank is 2. You get your rank is 2. Then there is a way to determine the independent columns. MATLAB has a code. It's given like this. You have to convert it to row echelon form and you will get the matrix R. Let us show. This is a matrix R which you get, and this is the pivot columns. That is one and two other columns. Okay. So what have they done is they have just subtracted. If you will subtract this row with this row, I hope it is clear. This is the first row, right? This is the first row, and this is okay. This is the first row, second row, third row, right? So what they have done, they have subtracted the third row from the first row. Let me do it. Let me just show. Q if you will see is 0, 1, 1, 1, 2, 1, 1, 2, 1, then 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. And what is the third row? This is 0, 1, 1, 1, 2, 1. 0, 1, 1, 0, 1, 1, 1, 2, 1. Okay. So what they have done is they have subtracted, they have done R3 is equal to R3 minus R1. So your Q matrix, you get it to be 0, 1, 1, 1, 2, 1, 1, 0, 1, 0, 1, 0. And since the R3 and R1 matrix are the same, it becomes 0, 0, 0, 0, 0, 0. Okay, this is the first part they've done. And now what they do is they interchange R2 and R1 because it is preferred that this should be 1. It should not be 0. So we can just interchange. So then we get the Q is now actually equal to 1 0 1 0 1 0 0 1 1 1 2 1 0 0 0 0 0 0. So now this is in row echelon form. Okay. So the maximum rank can be 3, and since there is one row which is all zeros, so these are all zeros, right? So the independent column vectors are actually given by this. So this is one independent column vector, and this is another independent column vector. 1 0 0 and 0 1 0. Okay, which is shown over here, right? So now we have got our columns. What is our columns? We have got 1 0 0 and 0 1 0. So now let us find another thing which will be independent of that. So if we have to find what is the T matrix. Check. T matrix we get. So you get your independent vectors actually are, you do this, your independent vectors are 0 1 0 and 1 0 1. Okay, these are your independent vectors, right? And what are your null vectors? Is null of Q and R. And then we get a new vector. Okay, we take the first basis vector. And then we get the T matrix is given by 0 1 0 1 0 1 and minus 1 0 1. Okay, so this is the new transformation matrix we use. Right. Now, when you do the transformation, okay, you do the transformation, what you will see is this is the transform matrix 0 1 1 1 0 0, and this is 0 0 1, and B transform is given by this. So what I wanted to highlight is that I have used different transformation matrix as compared to them, which is also an independent vector. Okay, I've used in a transformation matrix, but still my A transform and B transform matrix is coming out to be the same. Okay, they are still coming out to be the same. So if you will see what is the final transform matrix is, A transformed. Well, let me write better way. X. Okay, the X, or we can write it in terms of Z. Z actually is equal to this A transform, which is this is given by 1 0 1 1 0. So it is 1 0 1 1 1 0 3 1 0 0 1 1 0 0 0 1 0 0 1 into Z, and B transformed is given by 1 0 0 1 1 0 0 1 0 0 U, right? So this part and this part, these form what is known as the controllable matrix, right? And this is the uncontrollable part. These are the uncontrollable parts. Okay. So that is shown over here. Right. So this is the controllable part and this is the uncontrollable part, which here shown in this part. Okay. So ACC is the controllable part. ACU bar is the AUU bar is the part which is uncontrollable. And ACU bar is the cross coupling part. Is the cross coupling terms. Right. Okay. So now Let us go for the next part, which is complex eigenvalues in Jordan form, controllability and observability. Okay. So suppose we have a matrix x dot. This is 1, 2, minus 2, 1 into x. Right? This is our matrix. So what will be the eigenvalues? Let us find the eigenvalues. And let us say this is some b11, b12 into u. Something is there. So let's find the eigenvalues. So eigenvalues is what? Lambda I minus a. Okay. It is lambda 0, 0, lambda minus 1, 2, minus 2, 1. Okay. That comes out to be lambda minus 1, minus 2, 2, and lambda minus 1. So the lambda I minus a is equal to lambda minus 1 square plus 4. So it comes out to be lambda square minus 2 lambda plus 1 plus 4. Okay, it comes out to be lambda square minus 2 lambda plus 5. So can you tell me what will be these eigenvalues? Can you compute and tell me? Siva, Ratesh, 3B. What will be the eigenvalues of this? Okay, so we can find the eigenvalues given by 1 minus 2, 5. If you find the eigenvalues, you will get them to be 1 plus or minus 2j. Okay, so these are the eigenvalues, right? So you must observe this matrix very, very carefully. If you will observe the matrix, you will understand what has happened is. Let us write it in a better way. So this actually is equal to lambda minus 1 square minus 2i square. Okay. So this can be written as lambda minus 1 minus 2i into lambda minus 1 plus 2i. Okay. Right. That is why you get your lambda is equal to 1 plus or minus 2i. So this is why they are complex eigenvalues you are getting. And you must observe it very carefully. If you will observe this matrix, you will see that this and this are equal, and this also is equal, and this also is equal, but only there's this sign. Okay, this is not clear. Only there's the sign notation. So the values are the same, but the signs are different. Okay, so this is the Jordan form where you will get these complex eigenvalues. All right. So now we have to check what is the controllability. Okay, we have to check this controllability is dependent on what. Okay, so this is my A matrix and this is the B matrix, right? So let us do A into B. So that is what 1, 2, minus 2, 1, B1, 1, B1, 2, right? So this would be equal to what? B11 plus 2B12, and this is minus 2B11 plus B12, right? So the controllability matrix is given by Q. It is B, A, B. So what is B? Is B11, B12, and this is what B11 plus 2B12 minus 2B11 plus B12. Okay. All right. So now let us consider two cases. What is, will Q be controllable if B11 is 0? Then what will happen? My Q will be what then? So the Q1 in this case will be 0, B12, 2B11, sorry, it will be 2B12 and plus B12. And what is the determinant of Q1 in this case? It is equal to minus 2B12 square. Okay, it is minus 2B12 square. Let us consider the case when Q B12 is equal to 0. So this is my Q2. My Q2 in this case is B110 and B11 and minus 2B11. Okay. So now if you find the determinant of Q2 in this case, you will get it to be minus 2B11 square. So what is required? If I want my system Q to be controllable, B11 should not be equal to 0 or B12 should not be equal to 0. If both B11 and B12 both are equal to 0, then my system is uncontrollable. If B11 is not equal to 0, then my system is controllable. And if B12 is not equal to 0, then also my system is controllable. Okay. So I hope this part you understand. And this is very important. Okay. Because this is regarding complex eigenvalues. So usually many times we consider the eigenvalues are real and distinct. But in this case, the eigenvalues are complex. And it is from when you do the Jordan decomposition, you get it in this format. Okay, and once you get it in this format, what is the condition that it is controllable or observable? Okay. Now, let us consider I have got it into this Jordan form. Okay. It is in this Jordan form. What should be my I? What should be my Y? Let us say I have a C1 and a C2 into X. So what should be my Y? Such that the system is observable. Okay, so let us say we have to find what C into A. Right? So C is C1, C2, Y A is what? 1, 2, minus 2, 1. Right? So this is 1 row 2 columns. So it is C1 minus 2C2 is 1. Okay, so C1 minus 2C2 and then here 2C1 plus C2. Okay, so the matrix P, observability matrix is C and CA, that is equal to C1, C2, C1 minus 2, C2, and 2C1 plus C2. So again, let us consider what should be my C1 and C2. So two cases are there. Okay, P when C1 is equal to 0. That is my P1. So that is what 0 minus 2C2, C2, and C2. Okay. So what is the determinant of P1? It comes out to be minus 2C2 square. Right? Then what's the case when C2 is equal to 0? Then what is my P2? P2 in this case is 0. Okay. Sorry, P2 in this case is C1 and C1, 0 and 2C1. Right? So determinant of P1, P2 in this case is equal to 2C1 square. Sorry, 2C1 square. So what it means is I can have C1 equal to 0, but my C2 should not be equal to 0. Or I can have C2 equal to 0, but my C1 should not be equal to 0. So if it has to be observable, for observability, either C1 should not be equal to 0 or C2 should not be equal to 0. Okay, so this is the case. Right? So are there any doubts in this? Okay, so similarly, sir has taught about observability. He has gone in depth. How do we find the Wronskian, sorry, the controllability gradient, etc. Yes, taught, right? How to find the observability gradient? How do you find this matrix, observability matrix? How it is under linear transformation also, it is independent. Observability doesn't change even if you do linear transformation. That is why the transformation when you multiply by A, right? It also still remains what you say, observable or controllable with respect to any multiplication which you do. So this also sir has proved Gilbert's observability criterion. This also sir is shown, right? Okay, so let us consider Jordan form is a very important thing, which is also there a lot in the assignments. So let us consider Jordan form. Okay, let us consider Jordan form. So what is the Jordan form? Jordan form is like you have a matrix. You have a matrix, and that gets converted into some Jordan form matrix, right? So you have A and B that converts into some matrix. Let us say, make it simple, A Jordan and B Jordan. Okay, there's a certain transformation which is there, and you convert your AB matrix into A Jordan form, B Jordan form. Or Jordan doesn't look good. Let us say you convert into AJ and BJ, which stands for Jordan. Okay, so now your A matrix, let us say it has many eigenvalues. Let us take an example. It has -1 plus minus 2j, the one we have studied. It has the eigenvalue, let us say 3. It has the eigenvalues -1 comma minus. Okay, so these are the eigenvalues which are there, right? This, so how many I so there are how many eigenvalues it has? 2, 3, 4, 5. So A, it is a 5 cross 5 matrix, right? Now, and let us, for simplicity, let us consider U. There's only a single U. Okay, there's only a single U. All right. So my A Jordan form will actually be equal to, let me write it down as -1, 2, -2, 1. Rest all elements 0. Rest all elements 0. Near 0, 0, 3, 0, 0, 0, 0, 0, -1. It is complicated here. It could be, and here -1. Here again 0, 0, 0. Then this could this could be 1 and this could be 0, or this could be 0 and this could be 1. Both cases are possible. Okay, it depends. Sometimes it comes out in this format, that is the first format, whatever is in orange. The orange one, it means there's an upper diagonal one. That means there's an upper diagonal one. And the purple one, it means there's a lower diagonal one. Okay, so this is my AJ matrix. Okay, this is my AJ matrix. Now, what is the BJ matrix? So BJ matrix, let us say it gets converted to some B1, B2, B3, B4, and B5. Okay, into this matrix. Now, when do I say it is controllable? Okay, let us consider this subsystem, this part. Let me consider this part. So this part is the one corresponding to, so this subsystem is the one corresponding to complex eigenvalues. Okay, this part is the one corresponding to the complex eigenvalues. So in this case, if this has to be controllable, what should happen? We just now saw, right? We just now saw that either B11 should not be equal to 0, B12 should not be equal to 0. So again over here also, either B1 should not be equal to 0 or B2 should not be equal to 0. So if anyone B1 or B2, anything is not equal to 0, then this subsystem, the green subsystem, is controllable. Okay, it is controllable. If B1, B2 both are 0, then this subsystem is uncontrollable. Okay, so what is the advantage of Jordan form is we are decomposing a system, a complex system, into small subsystems, and then we are checking the controllability and the stability of the small subsystems. Okay, so that is the power which is there of this Jordan form. So now, so that's why we can get individually, we can know that which system is controlled by what input, and how do we retrace back the steps, etc. That is the possible using Jordan form. So now we have established that if I want to control this green subsystem, my B1 should not be equal to 0 or my B2 should not be equal to 0. So that is one point. Okay. Next point is, let us say this subsystem. Okay. So this subsystem is dependent on B3. So this is what corresponding to real eigenvalue. Okay. Real and distinct eigenvalue with multiplicity 1. Okay. With multiplicity 1. So in this case, we can say that B3 should not be equal to 0. If B3 equal to 0, this mode is uncontrollable. You cannot control this subsystem. But if B3 is not equal to 0, then you can control it. Okay, so for this part, B3 should not be equal to 0. Now for the challenging and fun one. Okay, this is the one which becomes interesting. So now this is the subsystem. Okay, this is the subsystem which we want to consider. So this subsystem is what? Real and repeated eigenvalues. Okay, these are real and repeated eigenvalues, right? And in this, there are two cases. In this, there are two cases. One is a purple case, and one is the red case. Okay, one is the purple case, and one is the red case. So in the purple case, what happens is if this is 1, okay, and this is -1. So if my B in the purple case, what I need is uh, B4 should not be equal to 0. And in the red case, what I need is my B5 should not be equal to 0. So now I have written it so that you can refer to it because I'll be uploading these notes and you guys have access to it. But now let us go in depth. Like, why do I mean this? Okay. This is a condition I'm just saying, but why you should believe it. Right? We have proved it for this first case for complex eigenvalues. Let us prove it in the case for real and repeated eigenvalues. Okay, let us prove it in that case. So now what I do is, this is my subsystem. I will chalk out this subsystem. I will just explore the stability of this subsystem. So Jordan form, I have made my entire big system. I have decomposed it into small subsystems. And now I'm going to check the controllability of this small subsystem, right? So let us say my x hat is given by, what is this? -1. Okay, let us make it much more understandable. So x hat is given by -1, 0, 1, 0 into x hat. This x hat dot plus b4, b5, u. Okay, and sorry, so this has to be 1. So this has to be 1. Right? So now if we will see this system, what we have, this x1 hat dot is equal to minus x hat 1 plus b4 into u, and x2 hat dot is equal to, this is -1 again. So this will be x1 hat minus x2 hat plus b5 into u. Okay, it is given by this. So now, what is the case? I told that b4 should not be equal to 0. So let us assume, if we assume b4 is equal to 0, then what happens? I can control my x2 hat. How do you know what you are controlling? You're actually controlling the rate of change, right? You're controlling the rate of change of x2 hat dot, right? Because b5 is not equal to 0. Through u, I can control the rate of change of x2 hat dot. But because b4 is equal to 0, I cannot control x1 hat. Right? I cannot control x1 hat. So that is why we have to make sure that it is essential that b4 is not equal to 0. Okay, this is proved. Now, what if b5 is 0? So what if B5 is equal to 0? Then can we still control it? So what our system will become? It will become x1 hat dot is equal to minus x1 hat plus b4 into u, and x2 hat dot is equal to x1 hat minus x2 hat. Okay. So now can I control x2? I can control x1 hat. So u controls x1 hat. And if you see over here, x2 hat dot is dependent on x1 hat. And what happens is x2 hat depends on x1 hat. So u is indirectly controlling x2 hat. Okay, so that's why the condition is that b4 should not be equal to 0. B4 should not be equal to. So that means if it is difficult to remember, understand this lower diagonal, upper diagonal, one should be 1, another should be 0, something like that is there. If you want to make it simple, if you want to understand, you have, let us say, it is given in this Jordan form, right? The one, that row in which there's only a single one, right? The row in which there's a single one, single element is there, that should be controlled by your input. If that one is controlled by the input, then the row above it, it will control. It will control that one automatically, right? Or the row above or below. That depends on which form you have written it. So in the case of the red case, right? In the case of the red case, what happens in the case of the red case? Let us write it down as x hat dot in the red case will be equal to 1 1 will be 1 1 minus 1 1 minus 1 1 0 minus 1, okay, into x hat plus b4 b5 into u. So in this case, what happens is this is the important one, that this is the important guy. This should not be equal to 0. So in this case, b5 should not be equal to 0. Because if this is 0, right, then this state, the second state will not be controlled. The second state will not be controlled, right? So I hope this has given you clarity into why there are those theorems are there, and they say that this value should not be 0, that value should not be equal to 0. So that I hope you guys have gotten some clarity with this, right? Okay. So this is about the Jordan form. So Siva Rutish, do you have any other doubts which you'd want me to clear? So that is why Jordan form, if you will observe, Sir has written, Sir has shown that in case the Jordan block contains ones in the lower subdiagonal, then the columns corresponding to last column of each Jordan blocks are non-zero. And in case the Jordan block contains ones in the upper subdiagonal, observable if only if the column of corresponding first column of each Jordan block are non-zero. Okay, so I hope this part is clear. Okay, so we have seen what is Jordan form, what is how to convert also into Jordan form. And similarly, you can convert a system by Kalman into observe yes found. You can show a system in this form. Okay, so this is the controllable form. This is a not controllable and observable form. And this is the controllable and not observable form. And this is the not controllable and not observable form. Okay, so you can decompose the matrices into this format. Okay, so effectively, what is the goal of these decompositions is there's a complex system. You are making the system into decomposing it into smaller subsystems where you know like which is controllable, which is observable, which is observable, which is not controllable, which is observable and controllable both, etc. So that is the object. Yeah, so I had given a MATLAB example of controllability, right? This is a A matrix, this is a B matrix, this is the Q1 matrix, Q2 matrix, both came out to be the same rank. right? Now, what would happen if I change B to 1, 1? Okay, if my B became 1, 1, let us assume that B has changed to 1, 1. Then if you run it, you will observe that both Q1 and Q2 have changed, and both the rank of Q1 and Q2 are the same. So what is the takeaway here? Takeaway is the rank of Q1 is equal to rank of Q2, right? Because it is a linear transformation, right? You are doing a linear transformation of the system. You have just multiplied it by some value. So that means what is your Q2? Your Q2 actually is equal to A into Q1. So that is not changing the rank, right? It is not changing the rank. Now, let us assume my Q3 is equal to minus Q1. Then will the rank change? I don't think it will change, right? We take Q3 is equal to minus Q1, right? This is my Q3. And you find the rank of Q3. If you run it, the rank of Q3 remains 2, right? So it is still controllable. That means when you have your controllability matrix, that is Q1, okay, you multiply it by multiplied by 1, multiplied by minus 1, multiplied by 5, multiplied by A, multiplied by minus A, still your rank will not change. That is what you must realize. Okay, your controllability matrix. That's why there are various matrices you can use, but your controllability matrix is that the smallest or the easiest, like you can say, the block from which you can actually check whether the system is controllable or observable. Okay, so now this is the way I have written the matrix Q1, B, A, B. And when you write this, you have to be very careful about the comma, where you use the semicolon. So the semicolon means I'm going to the next row, right? The comma means I'm going to the next column. So these are the things which I I have learned in MATLAB to use, and so I have understood, right? So suppose you have defined your matrices A and B, right? MATLAB has a command also. It has a command, right? And that command is controllability. It will find the controllability matrix, and you have to just give what inputs you have to give A and B. So if I do that, then what I will get this is the answer. My controllability matrix is 1, 1, 5, 10, which is same as my Q1 matrix. So there is a command in MATLAB to directly give you the controllability matrix given your system matrix A and your matrix B. And if I want to make it even simpler, right, what I do is I just find a rank. I just find a rank for the contributing matrix. It will give me 2. It will just directly give me whether this contributing matrix is 2. Okay. So this is how MATLAB has made my life quite simple in some sense, right? Similarly, I have to find observability. So this is C equal to 1, 1, right? This is the thing. Now let me know. I don't want to find the rank. These are two things we have established. So let us say this the C matrix is given over here. This is my C matrix, right? C matrix is 1, 1. What is the observability matrix? That is P. P is what? C matrix. And it is A into C, right? P, A, B. Actually, this C into A. Okay, so this is the P matrix. So let us find the P matrix. The P matrix is actually 1, 1, 3, 12. And I think we have got the same as well. And if you find a rank of P, you get it to be 2. The rank of P comes out to be 2. That means it is completely observable system. Right? It is a completely observable system. Now, as we have a direct command to find the contributing matrix, there's another direct command to find the observability matrix. That is OBSV. It finds the observability of state space model, and that you have to just give the matrix A, comma C. Okay, it will just directly give you. So this is P and this is the observability P. Both are the same, right? Both are the same. And you can just do the rank of the observability matrix. It will give you the rank. Okay. So this is something we got. Now what we do, let us change C. Let me make this 0. Then what will happen? Will it change? Let us check. You can see it has not changed. It has not changed. Even though I have changed my C matrix, even though I have changed one output, my rank of a P matrix remains the same. So what do we understand? By sensing in this configuration, if I will just sense my state x1 and I don't sense my state x2, still I can determine what is the my state x2. Okay, I can determine what is the initial condition. Let us see if it happens with the counter. If I only sense state x2 and not state x1, what will happen then? Right? In this case, it is not possible. In this case, it is not possible for me to do that. That is, only if I sensing x2, I cannot find what was x1 earlier. Okay, but if I sense x1, I can find what was x2, right? So that's the point I want to highlight over here is. So we saw the observability example. So this observability is only dependent on the A matrix and the C matrix, right? If I change them, observability can change. So what is C matrix? What is the significance of the C matrix? So in an actual practical system, you have an actual practical system, right? And you have an actual practical system and you need certain sensors. You have to send certain signals. So why observers became popular is because you cannot sense all signals. You may not be able to go inside a big tank and check, sense what is the temperature, etc. It's not always possible. So what they want to do is, if I can just send some outputs, and I know what input I am giving to the system, I can estimate what is the state of my system, that what is the temperature of the system, what is the voltage of the system. I can just estimate it. Okay. And use and how do I check whether I can estimate that properly is through the observability matrix. Now we showed that if your C matrix was 1, 1, okay, for the example which we did on MATLAB, it is observable, right? It is observable. That means in this case, my output Y was x1 plus x2, and it is observable, right? What does it mean? It means that when I'm sensing my output Y and I know what is my input, I can get what was my initial condition for x1 and x2. I can back calculate it. My estimator can get that value. It is possible. That is a definition of observability. Now I made the matrix C to be 0, 1. That means I'm only having Y equal to x2. Means I'm only sensing state x2. Here I am sensing what? State, kind of like I'm controlling or I'm observing both the combination of x1 and x2. Right? I am sensing the output, which is a combination of state x1 and x2. Right? So this can be possible if actually in the physical system I have x1 plus x2 happening, then I can sense it. Otherwise, I have to sense both states x1 and x2. So when I'm doing y to x2, it means I'm just sensing state x2. What does that mean? When I'm sensing only state x2, that could be some voltage, that could be some temperature, that could be certain velocity, it could be certain distance, it could be the displacement, etc. That I am only sensing that particular signal or that particular state. I can estimate what is the values of the other states if I am observing both the output and the input. Okay, that is what this means. That is what this observability means. But however, when I make it c equal to 1, 0, that means my y equal to x1. I am only sensing state x1, then I am not able to find what is my state x2. I cannot determine. I cannot find out. Right? So that is why you should like kind of have a way of of thinking in terms of the physical system. That is every time sensors, you cannot use every time sensors. But how do you select it? Which signal you have to sense? So in a practical system, if you have more number of sensors, means the cost increases, etc. So there are various things. Okay, there are advanced topics such as sensor fusion. That is the same variable they're sensing at different locations or something. They're merging signals and they're combining them. There are various techniques are there. Advanced techniques are there, right? But if you consider just like a simple basic person, lesser number of sensors you have, your cost will reduce. Okay, your cost is reducing, right? And when your cost is reducing, it is very important in terms of a product. But you should be able to estimate what are the other states, and you should know whether one state is going unbounded, whether it is creating an issue, etc. So that is what we can understand the significance of the C matrix. That is, you have some big complex two tank system or you have big complex RLC system. If you can sense one state, and through the knowledge of that state, that output and the input, can you estimate what was the conditions of your previous states? Okay, can you look into your system? Like, can you do an X-ray of your system and know what are the states of the system? If that is possible, that means you are able to observe the system. Okay, so that is the thing. Then controllability means you are able to control the system. It is possible for you to go from one state to another state using an input. Okay, that input can be as large as possible, as small as possible. It could be, and that should happen within a finite duration. Okay, it should not take infinite time. So that is the definition of controllability, right? Okay. All right. Then there is something known as the observability subspace. If the rank of the observability matrix P is equal to n1, which is less than n, then there is a n1 dimension subspace. That means if your initial condition, etc., is in that subspace, you're able to estimate the other things, right? Or there's certain limits on what you can estimate. But if your rank is n, then you're able to completely estimate the states of your system. Okay. Okay. Hmm. Okay, so there's the controllability gradient, etc. is there. And if you solve it for LTI system, you again get this A transpose B, B transpose A, E raised to A transpose, etc. All this is state transfer. So all this state transfer, etc., they are not important for us. We just want to know whether a system is controllable or it is not controllable, right? And the decomposition, etc., can be done. Then this. So I have shown this how you decomposition of uncontrollable systems into controllable and uncontrollable subsystems. Similarly, there is this thing. Okay, this is my A matrix and B matrix, right? So let us check this. So I'll go step by step. Let me comment out the remaining things. So this is my A matrix. Let me run it. So this is my A matrix. It is -1, 0, 0, -1, 1, and -1. So it may look as though it is in Jordan form. You may think that it is in Jordan form, and since there's none of it is 0, you can say that it is controllable, you may think. But if you observe the A matrix carefully, you will notice that this A, it has -1 and -1. That is, the eigenvalues are repeated. And when it is repeated, it has to be that form, that there should be at least one off diagonal element which has value 1, which is not there. So that means this matrix is uncontrollable. Okay. So let us just find the controllability matrix which is given by this, right? If you find this controllability matrix, that is Q, that is 1, -1, -1, 1. So if you look at this, you can see that the row R1, first row, and the second row, they are dependent. That is, the second row is the -1 of the first row. So that means this matrix is not a full, it's not a full rank. Okay, it's not a full rank. So you can find what is the rank. Okay, you can also tell MATLAB to do that. It has some method to find the rank, and it will tell you that the rank comes out to be 1. Okay, so from this we conclude. What do we conclude? That this system is uncontrollable. It is not controllable. So one mode is controllable, one mode is not controllable. Right? So let me add this semicolon. So if I put a semicolon, it will not show the output. Okay, we have already seen these. So that's why I'm putting a semicolon. Okay. Now over here, they're saying, where's the example? Okay. Check if the state transfer is possible. This is one example. The example was there of last year. So this is a question. Okay, so this is an uncontrollable system. Can these state transfers happen? Okay, so what do we do is we will define the initial and final states. Okay, this is the initial state x0 and this is the final state x0.5. Okay, let us consider that. So this is my initial state x0 and this is my final state. Okay, I will define the time intervals. So what are the time intervals? T1 equal to 0, T final 1 is equal to 0.5, right? Now I have to find out what is the matrix exponential. So that I will find out what is the matrix exponential. Then I have to find what is T final 1 minus T final 2. Okay, which is over here. I have to find that value, right? So I find that. And then I will check whether this difference can be found through this. Okay, so we will check. Let me run this section. This is the exponential matrix, right? And this phi TF1 is given by this, right? And what is the reachability condition? X TF1 minus phi is x01, right? So then what they are finding is whether, so if you will see this difference one, it is 0.3933 minus 0.3937, right? They are very close. And what is your B matrix? You will observe the B matrix, it is 1 and minus, right? So that means this is approximately, if you take 0.393 common, it is approximately 1 and minus 1, right? It is approximately 1 and minus 1. So you can use an input to bring it to this value. You can use an input to bring it to this value. But let us consider a case for the second part, or the third part, which is not controllable. That is, this are your conditions, right? This is your condition, initial condition, and this is your final condition. This is the time for the third case, right? And this is the phi matrix for that, and this is the reachability condition for that. So let us run the section for that. When we run the section, we get it to be okay. Let us comment on the first part, and let us see the output for the third part. This also is not required. Okay, let us run the section. So this phi t of 3, and this is a difference. So if you see this difference 0.3233 and 1.3233, it is not a multiple of the B matrix. Okay, you can't, it is not one, it is not scaled by 1 minus 1. In the previous case, it was scaled by 1 minus 1, but in this case, it is not scaled by 1 minus 1. That is why state transfer is not possible. Okay. So there's another way we can check is the rank of Q. That is given here. If rank of Q and difference of 3 and that tolerance. Okay, so if you have this Q and difference of 3. So let us see what is this Q and difference of 3. Okay, let me comment out this and let us just check this. What is Q comma difference 3? So Q is given by this 1 minus 1 minus 1 1, and difference of 3 is given by this. And what is Q? So this is Q. This is my Q and this is my difference of 3, right? So now this rank of Q difference in 3 and this rank of Q, they have to be equal. If they are not equal, then that means the state transfer is not possible, right? So that is what I am checking. That the condition is, if the rank of Q and difference of 3 is equal to this rank of Q, then we are saying that state transfer 3 is possible. If it is not, then state transfer 3 is not possible. And certain tolerance is required to be given because MATLAB by computation requires certain tolerance, right? So if we run this section, it will show us, okay, it shows tolerance. Okay, tolerance I commented out. Let us allow it to run. It shows that state transfer 3 is not possible. Okay, so this is one way to check whether state transfer is possible or not. But usually this concept or this requirement of state transfer is not important. What is more important is the system controllable? Is the system observable? You find the controllability, observability matrices. You find the Jordan form. This Jordan form is very important for you to understand, right? So this actually deceives us. This A matrix kind of deceives us. It appears to be in Jordan form, but it isn't, because they are repeated eigenvalues. So when there's repeated eigenvalues, there'll be an off-diagonal element 1. It could be in the upper matrix or on the lower side also, but they will be there, right? So now if I want to make it controllable, what I will do? Okay, what I do is, I'll add my off-diagonal element. Okay, so I'm changing an element to make Q full rank. So what I do is, I will run this part. Okay, let me run it over here. Or let me run it here. Okay. I have modified my E matrix. And I'll take my Q modified and check this. Now these I don't need. Okay. So I'll run this section. So this is my modified A matrix. So now I have added an off diagonal element 1. So now I've actually made it into my diagonal form, into the Jordan form. And then the Q modified comes out to be this and the rank comes out to be 2. Right? So this is an example. So you, first of all, you have to carefully observe the question. You have to understand the concept very well. That is, controllability and controllability means that the input has an effect on the state. Right? And if you write the dynamical equations, you can understand. And sometimes it is like very complicated. You don't know that which has effect on what has effect on which, or that it is not easy to understand. So for that, they convert it into Jordan form. And once you convert it into Jordan form, it is easy for you to see that which state is controlled by the input, which state is not controlled by your input. Okay. So are there any doubts? Miss, what is her name? Miss Siva Ratish. Any doubts?
No, sir.
Okay. So have you enrolled for the exam?
Yes, sir.
Okay. Mhm. Right. And like your PhD is in what topic? Like what topic are you? Is your project on or thesis on?
Sir, actually, we have talked before. I have entered from
Oh,
another
okay, okay. So
name
you're the
because
one in robotic mechatronics,
yeah,
right?
yeah, sir.
Okay, 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 fine, fine. Actually, that's why I was confused. Ah, I'm sorry. Yeah. Okay. Yeah. So then no queries. So I'll just take a brief recap and just give a brief recap, right? So like for an LTI system, if you want to find controllability, you use the controllability matrix. You find a rank. There's something known as the controllability subspace, which depends on the rank of the controllability matrix. And the rest of the dimensions are uncontrollable. Then how controllability depends on the value of A and B. Okay, it depends. If you modify the system, controllability can change. Then controllability very much dependent on A and B. And then if the uncontrollable system is there, if the uncontrollable mode or uncontrollable state is stable, then you can say that the system is stabilizable. If that mode or that state is uncontrollable, then it will go on to infinity. So you cannot actually control the system. You cannot even stabilize the system. Okay, so that's why we have shown that these modes are unstable because they increase with time, right? Similarly, there's an observability matrix. Okay, and again, this is the Q matrix for controllability. Then there's a Jordan form where you can convert it into Jordan form. So there you use these eigenvalues and eigen decomposition, you get the eigenvectors, and then you do the suitable transformation, right? After you do the suitable transformation, you get it in a diagonal form, which is shown over here. Okay. And then when you convert in Jordan form, you can actually see that U is connected to Z1, but U is not connected to Z2. If you are able to, visualize and you can actually observe. That's the power of Jordan form, right? So even after linear transformation, the system remains uncontrollable. That is, if you change a B matrix, if you convert multiply it by -2 into B, etc., it will not change. What happens is the controllability property of the system will not change. Okay, but this happens only if you are multiplying it by some linear transformation, not just you just arbitrarily change something in B. If you change, then the property can get altered, right? Which you have seen. Similarly, this is the observability matrix we saw. How do you do the decomposition? Q matrix, row echelon form, right? Then this is an important case. That this case is when you have complex eigenvalues. This is a complex eigenvalues case, right? So this is very like something you should be able to observe that 1 and 1 are the same and 2 and -2 are opposite signs, right? So this brings it in that way you can identify quickly that it is a complex eigenvalue, right? And their values, how do you find the complex eigenvalue also I've shown over here, and how you need to make sure B11 is not equal to 0, B12 is not equal to 0, something like this you have to see, right? Similarly for observability also I've shown it. Then the Jordan form, how I've made it into a certain block. So Jordan form is actually making your complex system into small subsystems. And then you can check which is controllable, which part is not controllable, which part is observable, etc. You can check individually, right? So this is the power of Jordan form, but it may not always be possible for you to convert it into Jordan form. That is there in Sir's notes. He has told. Okay, but for our visual understanding, for our understanding of the system behavior and dynamics, Jordan form is very useful, right? And what is the case? Like why, what should not be equal to 0, what should be equal to, what can be 0? That also I've shown over here. So you can easily refer to this. Yeah, I think this is very important for you to be able to understand and to solve, right? The assignment questions as well. Okay, so how I brought that from that system, I have taken this subsystem, and then we have shown what controls x1 dot, how x2 dot depends on x1 hat, and how u is indirectly controlling x2 hat. All this I have shown. Observability example in MATLAB we have seen, which depends on A and C, and how the C depends on the C matrix. So you have certain dynamical system, but what do you observe? What do you sense? But depending on what you sense, you can actually look into your system, know what are the actual states of the system. So that you depends on your C matrix, observability subspace, etc. Okay, so all this we have seen. Okay, so we can end today, and you can also submit the assignment, and you can also solve it. Yeah, and you can try your best. And if you okay, so Siva Ratish, I'll end the meeting. Yeah.
Okay, sir.
Okay. Yes, thank you. Hmm?